vectors in a plane? Yeah, so it's going to be a boring topic for many. If you've seen vectors before. Now we got our component form. If you're talking about points and the vector that goes between them, you got your initial point labeled as x1, y1. You got your terminal point where it ends, and x2 and y2. A vector has a angle it goes at. It also has a distance. Now, what's the distance called in vector notation? Magnitude? Yeah. That's a length, but vectors have their own terminology for different items. Sometimes I'll say length, sometimes I'll say magnitude, but realize that that's the official terminology. Yeah. Yeah, I'd be surprised if there's things here you haven't seen in physics. What is it? Okay, let's look at number 3. Number 3 says find a component form of the vector v. We'll do that first. And you can see the points we have here in the arrow indicating the direction. So our initial point is 1, 2. And from the formula, that was x1, y1. Our terminal point is this one right here, which is 5, 4. And that, from my definition, was x2, y2. Now this is a component form. So we'll have a less than. That's our symbol for the vector. And we're going to have x2 minus x1. So I'm going to have 5 minus 1, comma, and then y2 minus y1, 4 minus 2. 5 minus 1 is 4, 4 minus 2 is 2. And that's our component form. A lot of it is, yeah. There's not a whole lot of calculus in this chapter, I don't think. So, yeah, there's trigonometry. Second thing they asked us to do is sketch a vector with initial point at the origin. So, using our component form here, we're starting at the origin. Now, what would the 4 tell us if you've seen this before? Which axis? What? To the right. So right 4 and up 2. And now your graph. Yeah, you can. Right. Yeah, because this is our x's, this is our y's. So, yeah, up or right 4, up 2, drop 1. Now these say find the vectors u and v whose initial and terminal points are given. Show that u and v are equivalent. They're equivalent if your component forms are the same. So let's take a look at number 5. Now this bold, when you see a letter bold like that, that typically means vector. So u is a vector. And oftentimes when you see it written down, they put a little line over it like that, since it's hard to bold when you're writing. And we're going from 3, 2 to 5, 6. Initial, terminal. And our other one, our vector B, is 1, 4, and 3, 8. So our component form, we're going to subtract our x's. Again, this is x1, y1, x2, y2. So we're going to have 5 minus 3, and we'll have 6 minus 2. 5 minus 3 is 2, 6 minus 2 is 4. For this one, this is my x1, this is my y1, this is my x2, this is my y2. So I'm going to have 8 minus 1, and I'll have 3 minus 4. So it gives us 7 and negative 1. Let's try that again. My eyes got off. 3 minus 1 and 8 minus 4. I'll blame on my glasses fogging up. 2, 4. Yeah, you subtract the x's, 3 minus 1, 8 minus 4. Making it harder by trying to label everything. So are these equivalent? Yeah. Equivalent, they got same direction, same magnitude. Just because the slope that, changing x, changing y. Let's see if there's anything different here. Sketch it, write to vector in component form. Oh yeah, there is. Write it with a standard unit vectors I and j. So let's look at number I guess 11. What does that red mean anyway? What's a red mean? Yeah. Are those like the ones with video or something? Or are you red green colorblind or? Oh.
I think those are examples that they do inside the book. When they're talking.
Oh, okay. So they go along with the video or something like that?
No, it's when you're going through the textbook, you go through some examples and go through them entirely by explaining each.
Oh, they do. Okay.
When they're explaining how to use it.
I never have looked at back. I thought they just put the answers for all the odd ones, but I never have cared to look, to be honest. Okay, let's find our component form. So we're going to subtract our x's. This is our initial, this is our terminal, and that's important where which one's the beginning, which one's the end. So I'm going to take 6 minus 8, and I'll take negative 1 minus 3. 6 minus 8 is negative 2. Negative 1 minus 3 is negative 4. Now that's our component form. I'm going to show the long way here to do this, but then it's a very easy way. I can split this up as negative 2, 0, plus 0, negative 4. Going backwards, adding vectors together. You add together the first parts, the x parts, negative 2 plus 0 is negative 2, and you add together the y parts, second part, 0 and negative 4 give me a negative 4. You can also factor out a number, so I can factor a negative 2 out of here. I can factor a negative 4 out of here. We got unit vectors. And 1, 0 is one of our unit vectors. A unit vector, this one in particular, goes out in terms of the x direction, a distance, a magnitude of 1. This is represented by I. We also have unit vectors in 3D, but this is just 2D. In 3D, you have 3 unit vectors. Here we got 0, 1. Which goes along the y-axis for a distance or magnitude of 1. And this is represented by j. Which means over here, I can replace the 1, 0 as I, and I can replace the 0, 1 as j. Now compare our component form here to using unit vectors. So I'm going through all the work, what do you do? Put an I with the first part, j with the second part. Very easy to switch back and forth. This is a very useful form when you're doing calculations. This is kind of cumbersome to use. You can freely go back and forth between these. Besides that, everything else we're done. Is this brand new to anybody? You've all seen I's and J's for the most part? Okay. On this problem, number 17, we have our vector v is equal to -1, 3, initial point is equal to 4, 2. Then we want to find the terminal point. Now, terminal point is x2, y2. This is our initial point, which is x1, y1. Now our vector is going to equal to x2 minus x1, y2 minus y1. And that's just from the definition of the component form I gave you earlier. If we plug in these items, on this side I plug in -1, 3 for my vector. On this side, I don't know x2 minus x1 we said is 4. I don't know y2 minus y1 we said was 2. Now I can equate the first parts together, and I can equate the second parts together to figure out what my terminal point is. So I'm going to have x2 minus 4 is equal to -1, and I'll have y2 minus 2 is equal to 3. Here, take -4 over, becomes a +4, and I get x2 is equal to 3. On this one, take -2 over, becomes a +2, and you get y2 is equal to 5. So our terminal point would be 3, 5. Now here's the official. They got a little different notation. I don't know why they use P1 and P2 instead of X1 and Y1, but that's just our component form. The magnitude. You just take the square root of Q1 minus P1, your X value subtracted, squared, plus Q2 minus P2 squared, or that's just the square root of your component vector, the X part squared plus Y part squared. Notice the double lines here and the bold V. That indicates our magnitude or length of our vector. Distance. Down here, I mentioned this. If your distance is 1, it's a unit vector. That I and J I referred to. They give you some other items here. Length of V is also called a norm of V. Usually magnitude is the one I hear about, but you do see norm every once in a while in mathematics. And if the magnitude is equal to 0, if and only if V is a 0 vector. Now that does not mean it's equal to 0. That means that's a 0 vector. What's that mean? This would equal to this. Or 0i plus 0j if you put it in that form. So that's an important thing to note. A lot of people see this 0 and think it's 0, and it's not. It's one of these two forms here. If you go on to Calc 3, you do a lot with vectors in Calc 3, and that's a mistake some people will make. A lot of this is kind of latent framework for Calc 3 if you're going on to that class. And I suppose it's in physics if you're going on to those type of classes. Which if you're going to engineering, I suppose it's the main thing you're going to do, right? Calc 3. Okay, so 21. Remember, it could be in that form, or it could be 8i plus 15j. They both would be the same. This wants us to find the magnitude of it. Magnitude of V, the vector V, is going to equal square root of 8 squared plus 15 squared. 64 plus 225, I think. 289. 17?
Yep.
Okay. So 17 would be our answer. If it didn't come out perfect, you would simplify the radical as much as you can. Typically, approximations, if you're going to do much more with this, you need to have the exact values to carry it on in the calculation. Now, there's different properties that are associated with vector operations. Commutative, where you can flip them around if you're adding two vectors together. Doesn't change it. You can, if you do an addition, you can change parentheses around. Add two vectors, u plus v first, or add v plus w first. If you're adding a zero vector doesn't change the vector. If you're adding the opposite, so you got u and you got negative u. Well, that's the signs changed, and like if I had a 3 and a negative 3, it gives me 0, so it gives you the 0 vector. Does not give you 0, gives you the 0 vector. If you have the C and D represent scalar values, numbers. If you had like 3 times 5u, you could first multiply the 3 times 5 together and then multiply it times u. The distributive property. If you got a vector out to the side and you got two numbers, though they don't have to be numbers, they can actually be variables too, like x plus 3. But if you had like 3 plus 5, then you could take 3 times a vector plus 5 times a vector, and it gives you the same result, or vice versa. And that's what this is indicating. If you got a distributive property here where you got a number out in front and vectors inside, you can take that number and multiply it times each one of the vectors inside. Just what you might think. If you're taking 1 times the vector, that just gives you the initial vector, doesn't change it. The actual scalar 0 times the vector gives you the 0 vector, because you're taking 0 times each entry. So, most of this is just kind of common sense when you're working a problem. You won't even think much about it because it doesn't go against anything you already know. Okay, so let's take a look at number 25. We're wanting to find 2v negative 3v 7/2 v 2/3 v. Well, you just replace your vector notation here with actual vector, 3, 5. And then you multiply the number through. 2 times 3 is 6. 2 times 5 is 10. And that'd be my answer. This is where some people like this in the 3i plus 5j form, because then you just think of these as variables. So like on this one, negative 3 times 3i plus 5j, and I don't care which way you do it. It's entirely up to you. Negative 3 times 3i is negative 9i. Negative 3 times 5 is negative 15j. I won't finish these, but these would be the same thing. Questions on multiplying by a scalar? Let's take a look at number 27. U is equal to 4, 9. And V is going to equal to 2, negative 5. And I'm going to use I and J's because I really do like those easier or better. I think they're easier. 2i minus 5j. First thing is take 2/3 times u. So I got 2/3 times 4i plus 9j. That gives me 8/3 I plus 6j. B I'll skip over since it's just another scalar. 3 times b. Let's look at C, b minus u. B is 2i minus 5j. I put parentheses around just to indicate that's the entire vector, minus, do have to have the parentheses around the second one, 4i plus 9j. Just like in algebra, when you got a negative out in front, this flips the sign of everything inside. So it becomes a negative 4i minus 9j. 2i minus 4i is negative 2i. Negative 5j, negative 9j is negative 14j. And that's right. D. D is 2u plus 5v. So I'm going to have 2 times u. U was 4i plus 9j plus 5 times v, which is 2i minus 5j. First thing I do is I use the distributive property, take the 2 and multiply through, and I get 8i plus 18j. Multiply the 5 through. 5 times 2 is 10i minus 25j. Just like when you're working with algebra, you'd add together the like terms. Here you add together the like items, the i's. 8 plus 10 is 18i. Add together the j's. 18 minus 25 is negative 7j. Questions on operations? If you forget, I wouldn't take any points off. Now, some people are picky about that, but I'm not. Because you'll find that I'll get real sloppy. I'm trying to be real careful here at first, but I'll get sloppy pretty soon. And and I get really bad in Calc 3 because we're doing so many vectors that it's just, I forget to put the probably 10% of the variables. It is important. I understand why some people really focus on it because you're going into like physics. Having something to line over a vector is a lot different than just a variable or a number. So. Now these says use a figure to sketch a graph of the vector. So this helps you understand the concept, although you've kind of already seen it already. I'm not very good at these. So use your imagination. It can be. I've already screwed it up, but that's okay. When you write these down, they have to be the same distance or magnitude. They have to be the same direction. If you look at this V here, that doesn't exactly match my V, does it? That's what I say. Use your imagination on this. Like number 29. We got negative U. I guess I could just copy this. Let me do that. That's going to be a lot sloppier, but it'll be neat. Now, if U is going out this way, think of the directed distance we saw back in the previous chapter. Negative U would be going where? The opposite direction. So it'd be going over this way, the same distance or magnitude. So this would be our negative U. I didn't quite make it long enough, but. So negative just flips the vector and goes in the other direction. Okay, negative V, that just will go down. You were asking about U minus V. Now this goes out a distance of u. So like, let's say this was my starting place right here. And I go out this distance here for u. Now if I went plus v would be up like this. It starts where the other one ended. And it go the same distance as this, same magnitude, and same direction. And my resulting answer would be that straight line right there. This would be u plus v. Now u minus v. If we got a distance of u, where do you think the minus would go? Opposite direction. Yes, it goes down here. I can't go the entire distance because I planned poorly. And this right here is our u minus v. So, I don't know if you do much with those in physics, but oh, you do? Okay. Yeah, I think most of this chapter, I don't know if there's any calculus in the chapter at all, to be honest.
No, there should be. Yeah, they have cosines be yeah.
Or yeah. Okay, ignore the length of a scalar multiple. It's a theorem, so I thought it should be thrown in there. But here's the theorem to find a unit vector in a direction of v. So if you're given a vector and you want to find a unit vector in the same direction as that, this is how you do it. The unit vector is, again, a magnitude, a distance of 1. The reason why you do this is so you can use this in other applications. I don't know if many of you probably were. You just stop at the unit vector and say that's good. Maybe if you're talking about a unit circle. Okay, so let's take a look at 35 using that formula. Okay, so our unit vector is going to be the vector over the magnitude. Well, let's find the magnitude. It's going to be the square root of 3 squared plus 12 squared. It's 9 plus 144. 153. That's bad. 17. So it'll be 3 squared of 17. So our unit vector from our formula is v over the magnitude v. So v over the magnitude of v. So we're going to have 312 over 3 square root of 17. Now, when you got a scalar down below there, you want to one of two things: either put it clear out in front, which some books do, or you put it underneath each number. So 3 over 3 square root of 17, and 12 over 3 square root of 17. There, the 3's would cancel. We got 1 over square root of 17, and this will give me 4 over square root of 17. Multiply top and bottom by square root of 17, and I got square root of 17 over 17, 4 square root of 17 over 17. If I were to find the magnitude of this distance, this magnitude would be 1. That's how you find a unit vector in the same direction as your v. Mhm. I don't think there's anything really exciting here. I left this in here, a triangle inequality, and they have a couple of problems on it, but I'm not going to have that on a test or anything. It's not really that useful for our purposes. If you go on and prove things in mathematics, like you plan a minor in mathematics, it's just worth taking a look at. Our standard unit vectors we talked about already. Talked about how I and J help us write it in different form based upon the standard unit vectors. Here's another way of writing it for a unit vector. You put it in terms of your angle, cosine theta I plus sine theta j. Specifically, this formula down here. Moreover, follows any non-zero vector v making an angle theta with a positive x-axis has the same direction as u, and you can write it as v is equal to the magnitude of v times the vector cosine theta sine theta equals the magnitude of v times cosine theta I plus magnitude of v sine theta j. So different ways you could write that. These problems say find a vector v with a given magnitude in the same direction as u. Okay, so 45. Magnitude of v is 6. And direction is u is equal to 0, 3. Now, I give you a hint on this down at the bottom. First, you find a vector v with a given magnitude in the same direction as another vector u. And how you do that is find a unit vector of u. U, just because it's labeled as u, does not mean unit vector. If I took square root of u, 0 squared plus 3 squared, that gives me 9 inside the square root, which gives me 3. So this is not a unit vector right currently. So our unit vector is going to be equal to u over the magnitude of u. So I'll have 0, 3 on top, and on the bottom, magnitude is a square root, then take 0 squared plus 3 squared. I guess this one's kind of a trivial one. Zero squared drops away, 3 squared is 9, square root of 9 is 3. And then if I broke this up, 0 over 3 and 3 over 3, it'd be 0, 1. It won't always be 0, 1. I just happen to pick the easiest one. The reason why it's probably 0, 1 is because one of them is a 0, if I had to guess. Now after that, then you multiply the magnitude by the unit vector from step 1. So you take 6 times 0, 1, which gives us 0, 6. And what that represents says find a vector v with the given magnitude and same direction as u. So it's going in the same direction as this vector here, with this magnitude, this distance. So does that make sense? Again, where you use this at, I have no clue. Some of this used in Calc 3 if you're going on there, but in terms of physics, it's been 35, 40 years since I've had physics, so I don't remember. Okay, let's take a look at 49. It tells us our magnitude of V is equal to 3, and theta is equal to 0. Now it says find a component form of the V given its magnitude and angle and makes the positive x-axis. And that's given by this formula that I referred to earlier. So we're going to use this formula here. So you just plug in your values. The magnitude we said was 3. Cosine of theta, which is 0 degrees, and sine of 0 degrees. 0 degrees, think of my unit circle. Cosine of 0 degrees is 1. Sine of 0 degrees is 0. Multiply the 3 through, and I get 3, 0. Now, if it's an angle that's on your unit circle, you just give the exact value. If it's not on your unit circle, then you just plug in your calculator, making sure you're in the right mode. For example, 150 is on our unit circle. 120 is on our unit circle. 3.5 is not on our unit circle. So on number 52, I just plug that into my calculator. Questions on finding the component form given that information? Just a different way of finding it. You know, we looked at finding the component form at the beginning of this section where we were given 2 points. You just subtracted your x's, subtracted your y's. Well, this is finding a component form when you're given the magnitude and you're given the angle that it forms with the x-axis. Questions on any of that? Well, we'll stop there. We're done with 11.1.